Hello? Tamara. I need Tamara. Tamara is yours. Hey, today class is happening at QBP or UML? Okay, I'm here. I'm here. I'm hearing QBP. Come. Say,
too. I don't know about that. No, they we're going to follow lecture. It's longer than I expected. Do you have an email for this last hand? Wait a second. Are you the one the lady, the to the right? No. There's somebody who needs to contact. I'm just it's not going to project for 4 hours. And it still came back on the certain files turning. And that's 6 hours. 6 hours. So I got that message saying that this is on S. So set up your account. So I got an email and he said, well, don't delete anything. It was too big. I already deleted the first one. If I can get you one of the meetings done.
Do you guys face some problem of kicking out from the line?
Huh?
Face some problem of kicking out of this line, like when we submit a job, you have been automatically terminated.
I haven't been getting terminated here. I submitted a job with resources. I have some trouble with, at least, okay, am I looking at the wrong place where you can just start and see something's completed?
Yeah.
That's where I should be looking?
Yeah, it means like the nodes required for the job is down drained or it's under other priority.
Okay.
It's always kicking you off that line.
Oh, because like my thing is I look in the SRM file and VASP is always terminating without completion.
Without completion, me also have noticed that. Yeah.
Well, one's for you, but I increased my resources. I was doing 10 nodes, 240 CPUs. I ran one heat, 300 Kelvin.
So are you trying which one, like the batch Cori regular one or Cori S Cori debug?
For debug will time about 30 minutes. You can't use debug for more than I think 1, maybe 5 files at once. You have to be using regular premium NG or worked So I've only been using regular.
Regular itself is 2, no? Regular 1 and regular.
I just been modifying the batch file directly. But you know, I tried to increase the time to 96 hours, and that's when keeping back insufficient resources available. But you've been having troubles with the jobs determining.
Yeah, not only me, like me and QD was trying to calculate, submit the job. So every time we'll be in the line, we are suddenly kicked off the line. Then again, we have to resubmit again. So,
I mean, we're running out of time for a huge project. I'm very people are just running this like unit block like to the right, doing it. At least that. log in and everything. So, have you got any file that you terminate normally?
Any like adjustment manual?
Yeah.
Haven't.
I increased it to 24 hours, 10 minutes, 240 CPUs, and it still ran out of time.
What are you?
Well, you can get a file, it's a full electric diode with a junction, 320 some odd atoms. I know it's big, but pretty reason it's taking longer than it should. So.
Yeah. Not sure why.
Okay. So I guess like I'm only remembering in-car key points, postcard.
Have you been copying over the con card to a POS card each time you do
No, I just well, from the first model, I just copied over the comp card directly.
it? Okay. And then like how many times have you run or tried to get it to?
I actually only run 3 because I didn't want to keep wasting resources and keep just banging blocks together.
Did you start with the same POS card each time?
Yeah, it was the same POS card that started each time.
So even if it doesn't like germinate normally, it'll still update the con card with more
data.
So
Yeah, so don't waste those and don't blow them away.
well, when you finish a run, if it doesn't finish, copy your con card to a POS card. Get it started again. Use those.
At that point, they'll be reused in the next cycle.
Yeah, they'll be closer to what like the relaxed thing should look like.
Okay, well, this is still just trying to get through heating.
Oh, through heating. Mine's still sitting in the queue. Because
I guess I wanted to do 3 heatings. I know the heating you wanted me to do was 1,000 Kelvin, but so far nothing I've gotten is it's a 300 Kelvin file, so I don't know what I'm going to do with it. But that's the one I could reasonably run. I can get something like thermodynamics done with 27.
What's the heating temperature normally?
Huh?
Heating temperature.
Originally I wanted to do 300 Kelvin, 600 Kelvin, and 1,000 Kelvin. 300 Kelvin, 600 Kelvin are normal operational temperatures for the system.
I am giving 3 different heatings for the single heating.
3 different heatings. That's why I started the con card 3 times. And that's why I was able to submit new jobs each time rather
Why do you need 3 different heatings?
than I was just trying to do it because of those are the normal operating temperatures for electric diodes. To look for stability, to look for variations or changes across the temperature range. But if I can only get 300 done, at least it'll give me some points that say, okay, if I do proceed with research outside of this class, have I made what I can make, or is this what I do? Or is this looking like what I want to make? It's kind of where my report's going to have to go. Because I had no research coming into this, that's why I'm even looking into this thing.
Do you have account in CPAS?
I do an account in CCAS, but I don't know how to use it. I'm running with my head cut off just from the months of giving us in class. I set up the account for the nurse circuit. I set up the account for Corey, but I don't have mass access to their account, so I have to use.
CPAS, there is no box.
there is that you need to.
You can purchase a license for, which is like $3,000. And being as this is my first foray anywhere in this field, it's not. It's kind of.
You like
You have to pay for CPAS.
you masters do, and then you can be included with them.
Yeah.
If you work with them.
But it's a lot of paperwork, a lot of licensures that have to go into it, so.
Who's your advisor?
So okay, so if you don't mind, I'll put them in my mess. So for the next one, just submit a job again with heating and just copy the comp cards and postcard. Just try it somewhere.
With it, since I don't have as much experience with heating, this is the first time I've done heating. I'd ask Dimitri before
See, the heat and the molecular dynamics temperature has to be safe.
I guess, how many jobs did you guys been submitting? Because he asked me very specifically which account I'd be using and which name for jobs I'd be using.
I've been doing quite a, not like a whole lot, but I have 4 sitting
You guys are doing
Once Chem need to kick me out.
stuff like you and us.
Yeah, like you. Computer is behaving
Like me?
fingers.
I'm not kicking you.
You should behave more like Tamara. You should have a good heart like Tamara. Everything. Otherwise, she's like terrifying.
Kevin, long time no see.
Saw you on Thursday, what are you talking about?
That was way too long.
Is that a good question?
Like in some of the movies.
I guess.
Very good.
Wait, what is your name, David? Yeah, getting good chance to get it off.
I'm the one who's really from electrical, bachelor at Anderson. And fast. Goes on the bed the whole time.
Okay, so I'm able to make like density of states, atomic spectra. My two, what was it? Yeah, atomic dispersion spectra, density of states.
What kind of heat?
I'm not doing anything with heat.
Oh, you're just looking at the ground state.
Yeah.
That's much better.
So, yeah, I'm very like new coding stuff, so I probably wouldn't help. All I have to do is like show what's like work for me, and the graphs and what I've done so far. Okay, so I'm working on like 6 models, 2 of them are NA domed, 2 of them are iodine domed, and 2 of them are like domed. Is that same usually?
No, right now we only got one model. Yeah, I'm saying it. What I was gonna do is we're gonna keep it every time.
Need.
Yeah, so when I build 6 models, yeah, like I said, I have this about atomic, my 2 atomic spectrographs, and my momentum dispersion. those 4 things I'm doing were all 6 of those things. So I'm trying to find all of them like, today, and then tomorrow I'm gonna talk with you and figure out how to interpret them. Or if you're like well versed, maybe you can like.
I'm not well versed.
Okay, if it helps, I can share with you code that work for me and really my next year states. I'm telling, my 2 hours time is correct, and my
What was this, was this for class? Yeah, probably.
If it helps, primarily in medicine, it's like less precise than coding, but it may be faster for you.
That's it.
And so you have the problems.
Well, just, it never actually.
Okay. You know what, why do I download or remove the external, we can put these models together? Okay. Yeah, do that and then come back, I should have it downloaded by then.
Send, yeah.
I don't know.
Thanks for coming. Thanks for waiting. Thank you for your continuous effort towards completing this course. We will complete all academic parts of the course today. So feel free to stop me, but I will try to run like a marathon and squeeze in. Last time we did try to squeeze in. Who is it? Oh, okay, Mary. So last time we tried to squeeze in 2 lectures into one. It was not very successful. So today it will be even more ambitious. I will try to squeeze 3 in 1. And we should finish it before 8. What are we going to do in the rest of semester? So tomorrow we'll complete. Tomorrow we will complete all the things needed for projects. It will be really great if you will have 2 things ready by the time of the meeting here. Molecular dynamics in whatever configuration you need, and partial charge densities before and after molecular dynamics. Okay? And it's okay if you generate more than Kolmar and Sluma. Typically by the setting up energy interval, you generate more, right? So we will, so Lipti is not here. That's okay.
What you just said about molecular dynamics, does that apply to me too?
Yes. Oh, yes, yes. Hi, Lipti. How are you?
Yeah.
So, molecular dynamics and partial charge densities. if time will allow, so we will dedicate time for plotting charge densities in a new way, integrating over X and Y, right? For molecular dynamics, we will go over the movies, and please wave hands if you don't have access to VMD. So everyone has access to VMD, right? Consider to bring your personal equipment, like laptops with either VMD or connection to server or VMD is installed with you, okay? Yes?
These computers have VMD installed.
Oh, good. They finally followed my request, but it's a little delay. I asked you to do it by the beginning of semester. Maybe they miscounted and did it by the beginning of the next semester. It's good. It's good. Then I'll let you become a little easier. So on the coming Thursday, we will not do computational chemistry. It will be like technical writing meeting. So we'll discuss how to organize your data. You have, some of you feel that you don't have time to complete the project. You have so many problems staying in front of you, challenges, complications. But on the other hand, as time passes by, each of us is generating so many data that very soon, or maybe it's already too late, there is so big amount of data that it's hard to organize. And we will discuss how to organize, how to connect them by logical connections, and how to describe them right. And on Tuesday, in a week from now, please consider to bring final, or if you will not final, but final to your understanding versions of your written reports, combining like all accumulated data and some hints from our Thursday meeting. Then next week, Wednesday, there will be the last lab at all. I will just come here to help tie loose ends if anything is still missing. And on Thursday, May 2nd, there will be problematic to hold a lecture because it would be an important seminar, and I'll announce it and invite everyone to visit it on account of lecture. It will be about the same time, maybe an hour earlier. I'll announce it. And in 2 weeks from now, here, this room, we will have presentations. So I'll ask you to submit. Well, which time do you like?
Because I think I have another class.
No. The administration makes sure that exams of different classes do not overlap.
Like the exam period.
Yes. So your presentations will be counted as oral exam for the class. Okay? And I'll ask to send PowerPoints like night before. Good? Okay, I need to bring up things and start presenting. Did you get the slides in the email? Or link to the slides? So while the system is setting up, oh, okay, it's setting up quick. And I will, right now we shouldn't worry about it, but when we will approach to the time of presentations, I'll check if about your other exams. If there will be no overlaps, we can start a little earlier, not at 6, but right at 5 or at 4. But it will be based on everyone votes. Bless you. Is the question?
Yeah. So we keep getting kicked out of jobs or something.
Huh?
Getting kicked out of jobs or something.
Oh, when did you get it? Today or
I
yesterday?
did in the morning, early this morning, and I tried in the afternoon again.
Send me the link to your directory.
Yes.
Which is the
I was checking if there was a voice feedback. Okay, so we are about here. We covered all the plan about density metrics, and we are going from concept of density metrics to actual time-dependent density function theory, which those of you who need excited states may look tightly in. Nathan uses something more advanced, many-body perturbation theory. And if we will be successful today, we will cover TDDFT flowchart. And then next time we'll go over the writing, then editing your drafts, final drafts of the written reports, and then there will be presentations. Here are the projects. Mead does photofragmentation of polymers. Nathan does p-doped silicon gauge. we may have some discrepancies, but to my understanding, he's doing combustion of methane in oxygen. We can.
As far as I know.
Okay, very good. So we do not have discrepancy on subject. Okay, very good. And it's really challenging reactions because it needs a lot of activation energy to launch, to break this methane to carbon bonds. NS does PMMA properties. Sorry, I didn't answer your email, but we will do some elasticity of and two threads. It's not small because we are considering boundary conditions. So Dicta does ionic mobility. I don't know about if conductivity will be inserted, but mobility for sure. Ben does charge transfer at interface of organic and organic. Kevin does novel materials for thermoelectrics, lead telluride nanowires, and Kurt does a prototype of the PN junction that generates electricity. In some sense, his work is similar to Nathan, and in other aspects, it's similar to what Kevin is doing. David does two-dimensional perovskites, which are expected to be extremely efficient light emitters. Mary does polymerization of epoxy resin. And I still do not know how to interpret this PAJ, what does this acronym stands. I hope that in some time Queenie will teach all of us how to call this polymer. Okay, and those are from previous years. So everyone agrees in comparing electronic properties before and after thermalization, putting something into table, and tomorrow we will go over the script. Here is the name that converts the per charge files into integrated data that will be called lowercase per charge. And if one draws this post-processed version of the moleculars, they will be really helpful for interpretation to those of you who are looking onto charge transfer. Ben for sure, Nathan for sure, Kurt for sure, and others may benefit as well. So like three-dimensional orbitals are reduced to one-dimensional distributions, and it gives additional degree of freedom to analyze them. So I will scroll through things quick. You may just lean back, relax, as usual, as I recommend usual. Hopefully you're not listening to me. And I will give you heads up when you need to concentrate. It's physically impossible to concentrate on everything because I will jam a lot of information. So this was DFT flowchart. Last time, for a few lectures, we considered spin polarized version of LDA. Correction is based on gradient. And then we went to alternative way of including density into the flow chart loop of density functional theory. So density of electrons at each point can be generally formulated as a product of pairs of orbitals, different orbitals, with weight coefficients. And these orbitals generally do not need to be coinciding and do not need to be occupied. And then in this notation, there will be 4 segments, segment for occupied, segment for unoccupied, and segment for transition densities. Today we will see that the occupied part of density is of lowest order in incident electric field, and the transition density is the only thing that people take care when trying to take into account optical excitations. So it is a little example, and we will use it again and again today. So it is density matrix that translates pairs of orbitals into total density. So they are weighting coefficient, with which weight coefficient given pair of orbitals converts into total density. Okay, it's repetition of what we did. Nathan and Kurt may still know what is Bless and Vahak, and the rest of us do not need it. Kidding. If any one of us want to program, maybe we'll need it. And there is an abbreviation of transition density, which corresponds to like current transition from transition of occupation from conduction band to valence band. When we will call it X, and when it corresponds to emission, Y. So today we will go over equations for this X and Y. Okay. Then specifically for those who are interested in polarons and spectroscopy of small molecules, we consider this nuclear reorganization and Stokes shift. And this is the thing that we will practice tomorrow. Some of us will benefit it for the okay. The rest of the meeting will not be recorded because this public station is out of memory. Sometimes the tech support director sets up general recording, but there is no guarantee that it will work. So we will integrate and analyze the orbitals. And here is the summary of the way how we take into account spectra before TDDFT in the independent orbital approximation. So you do have concept of transition dipole moment, which has three components because it is three-dimensional vector. And if you take absolute value square, which is scalar product of this vector to itself, it will give the oscillator strength. And as soon as oscillator strength is basically transition dipole squared with some coefficients. So this structure is naturally connected to Einstein coefficient, and it gives us the rate how quickly occupation from occupied orbital can migrate to unoccupied orbital if or overall ground state can be converted into excited state if the system is being irradiated by oscillating electric field. So this is an equation that we all practice, right? So transition energy should be in resonance with frequency of incident light, and each resonant transition is weighted by the value of oscillator strength. Okay, and this is how transition energy shifts. We have no one fainted. Okay, then it is simple material. Joe. So you stopped me here, right? And we are going forward. So some of you may have heard about plasmons. Who did? Who never heard the word plasma? Okay, who did heard the word plasma? 1, 2, 3, 4, 5, 6. Okay. Plasma? Yes. Good. So if we have truly a large amount of electrons in metal particle and they are not confined to specific atoms, they move as a free electron gas inside metal. And incident electric field can move the electron density forcing back. And this collective electron motion may help for system to absorb energy. So these plasmons are based on classical electrodynamics. And we need this concept only as the intellectual step towards percepting the concepts that we are going to cover next. So that there is a no? There is a connection between motion of electrons inside your quantum system and deriving electric field. So if there is an incident electric field, it makes electrons to move. If it is structureless container and all electrons are just classical charges, they will move forth and back. Right? Oscillate with the same frequency as incident electric field oscillates. But in case you have quantum system with a gap, with specific states, with orbitals localized on specific atoms, the collective motion of electrons will be not so collective anymore. It will be something more discrete and more quantum. But there will be analogy between this classical electrodynamics motion of all electrons and pro-motion of electrons from ground to excited state. The connection is as follows, and to my memory, it is the last slide we covered. Last slide we covered before departure previous time. Should I care about setting up recording by independent things, or you don't care? Who needs recording? Who doesn't need recording?
Even for this lecture?
Yes.
Yeah, I would like a recording.
Okay. Then
Same here.
okay, I'll set up something real quick. Okay, so so it's a lot of cooperation. Whew.
Actually, more damage to the molecule itself. It's just
Okay. So I need to go quicker and quicker. So what is important in the excited states? The
Oscillation bands.
not bad. There is a
Or
connection.
the strength, the oscillator strength.
Oscillator strengths, yes. But if we have all the details, like oscillator strengths and other things, there is oscillation of overall density of electrons in quantum sense, similar to overall oscillation of density of electrons in classical sense. In both situations, they will oscillate with the same frequency as inducing field. Because if field is strong enough, it will be stronger than anything else, and it will make electrons to move forth and back, to make some motion. And there will be not wrong to say that amplitude of oscillations of the density of electrons will depend on frequency with which we excite the system. And it will depend on, in different positions, it will be different. So in some sense, and based on the background that we covered before, we are looking for a theory that will cover, that will, the dependence of this transition density which corresponds to, so to say, current change of the density, as function of position and frequency of incident field. And there is another question that we need to answer. At which frequencies of light transition from ground to excited is more reasonable? It's possible to happen. So we are going to skim through the concepts that typically carefully processed in the time-dependent perturbation theory. So those of you who already taken advanced quantum or who is looking forward to taking it in the future, this is the theory that is behind TDDFT. And in this theory, one looks on the correction terms for the observable in response to strengths of this perturbation. So we will look for the x and y terms. So here is my favorite picture, and if you are doing something else and if you are enjoying other activities or relaxing, I recommend to wake up and concentrate on this picture. If I would have the touch screen option, I would draw it, or probably let me show it here. So this is oversimplified summary of any excited state theory. If you feel comfortable with this image, then the rest of not very long remaining part of the course will be just technical details. So let's concentrate together. The left part and right part shows different presentations. So we are being born again today. Before this instant, most of us were thinking on the paradigm of excited states as occupied and unoccupied orbitals, right? And these little arrows are possible channels of system being converted from ground to excited, right? So one of the channels is when we go from highest occupied HOMO orbital to the lowest unoccupied, lowest transition energy, arrow 1. Another possible excitation is going, for example, from highest occupied -1, second lowest, to the LUMO, right? Another option is going from HOMO to LUMO +1. And the fourth option is going from HOMO -1 to LUMO +1, right? So if there are total 4 orbitals, which is a simplification, and 2 of them are occupied, 2 unoccupied, the system will have 4 lines in the absorption spectrum. Yes?
Why isn't HO -1 to HO possible?
Can I sit on your chair right now?
No.
Why?
Occupied.
Because it is already occupied. Same here. From HOMO -1 to HOMO is not possible because HOMO both are occupied.
Okay.
Who is guilty for that? Each problem has first and last name.
Pauli exclusion.
Exactly. Yes. Pauli exclusion principle. So you did answer your question yourself. So 4 transitions, right? Between orbitals. Now, I think this is a catharsis. This is a top point of the whole course. Most important 30 seconds. We are coming to a new way on looking on the excited states of the overall global system. When all occupied orbitals are occupied, when we are in a ground state, this is a one state with one total energy, right? And this is most orthodox way to think about system, not about individual orbitals, which are just auxiliary quantities, but overall energy of ground state. Now, we can follow little intricate details how the excitation happens, but from the side viewer, from experimenter, from the point of view of observations, we have just first excited state, right? With a certain transition energy. So if we excite system with so much h bar times omega energy, then system will go excited. There is another excited state, number 2. There is excited state number 3, excited state number 4. So each of these excited states can be decomposed onto pairs of occupied and unoccupied orbitals, but not always one pair. But correct way to think about excited states is one ground and several excited states. Please ask questions if you have, if you do not like this idea or if you need comments. Yes, please.
Why is it called the excitonic picture?
Because the decomposition of a given excited state over orbitals can be done slightly different than these pairs of orbitals and can include, so in this picture, one naturally takes into account interaction between electron and hole created in the excited state. If we are staying in this picture, it is barely possible to add excitonic corrections. Here it is very natural.
So are those 1, 2, 3, 4, do those energies correspond to the energy of a exciton?
Yes. So in absence, or if excitonic effects are negligible, so in a simplified way, the transition from HOMO to LUMO corresponds to transition from ground state to first excited state. In absence of excitonic effects, the transition from HOMO -1 to LUMO will correspond to second excited state, and so forth. Okay? So, but generally, the first excited state may have a little admixture of HOMO -1 to LUMO, of HOMO to LUMO +1. Especially if the energy offset between these orbitals is not so big. If there is some degree of partial degeneracy, right? So this is ideal, very good picture. Okay. So what we just discussed. Transition energy between HOMO and LUMO approximately equals to energy of first excited state. Or better to follow logic this way. Energy of first excited state is approximately equal to energy from HOMO to LUMO. We will cover this aspect in details, in more details. Okay. So, who has seen this equation in the past?
Yep.
Who? Where did you?
Yeah.
Okay, who else?
Looks familiar.
Okay, who never saw this equation or something similar? That's good, do not hesitate. Nathan?
I haven't seen that specific one.
Okay, so how would you call it? Yes, it's generally correct. It belongs to the class of eigenvalue problems. In what you are doing, it is related by its benefits to community to the Bethe-Salpeter equation, but it is lower level and higher computational throughput. But it is analogous to Bethe-Salpeter. So this equation. And we do not have time to derive any tiny bit, and it is very much abbreviated. So this eigenvalue equation generates transition energies, so at which energy system is able to accept energy, right? This equation has unknown vector in the left and right part, column vector, and it is composed of x and y. What are x and y? Yeah, those are transition densities corresponding to excitation and emission, right? Transition density. And density is generally a matrix, but we record them into a column. So if this equation is solved correctly, it provides transition energies and transition densities. It was community effort to design an equation by several independent people, and one of the contributors to its design in this form is Mark Cassidy, who right now works in Canada. So if you click on the drop-down menu in the Gaussian for TD-DFT, the Gaussian will solve this equation for you and give you a list of transitions. What we do know about these equations, we do know what are these symbols, what is this symbol, we know what is 0 and 1. Here, since it is matrix form, it will be unity matrices and zero matrices, and we do not know what are those A and B. So we need to make a connection between standard notation that we used during the course and this A and B notation for TD-DFT. As soon as you get it, you'll be accomplished computational chemist, at least in the applied side. So you'll be able to do state-of-the-art computation and publishing competitively, just explaining what you do in different software. So we are not doing derivations, but we are covering and making analogies to previous material in the course. Do you see anything familiar in this slide?
Rocket.
Yes. So what are these brackets mean?
Wait, is the numerator the Slater determinant?
Huh?
Is the numerator the Slater determinant?
It is similar to Slater determinant, and it originates from Slater determinant. But here it is a contraction two pairs of orbitals. It's not Slater determinant goes over all orbitals that contribute to electronic state. And here we pick up just few of them, just 4 of them. So we did cover these notations when we went over Hartree-Fock theory. So as you may remember, the interactions between we don't? Do we remember this notation? So not quite. So the interactions of electrons originate from Coulomb's law, right? So it is always in the denominator, 1 over r minus r prime. But since our electrons, if it will be classical electrodynamics, it will be just point charges, Q1, Q2 on the numerator. But since it is quantum particles, we do have the products of pairs of orbitals. And if we would consider only Coulomb attraction, it will be coinciding orbitals, given density. So this and this coincide, this and this coincide. And then it will give Coulomb term, right? But due to quantum nature, pairs of these orbitals may have different indices. And due to antisymmetry of the wave function, due to Slater determinant, thank you, Kevin, for establishing connection, for seeing this connection. So due to the fact that overall wave function is Slater determinant, the contributions to total energy originating from Coulomb interaction do have antisymmetric combinations of orbitals. And these contributions give rise to the matrix B and partial matrix A. The leading term in the A matrix will stay here even if we disable Coulomb interaction, if we assume that Coulomb interaction between orbitals is negligible. And it is one of the things that it's not the most important top thing in the course, but it is worth of looking at and focusing. So assume that our electrons do not have Coulomb interaction between themselves, and then the A term for Cassida equation will include only differences between energies of orbitals. Make sense? So if we scroll back into original equation, so matrix A stays on the diagonal with in original form and with conjugation. So in absence of Coulomb effects between electrons, matrix B goes to 0, and matrix A will be diagonal matrix, or differences between energies of occupied and unoccupied energies will stay on the diagonal. And if you diagonalize such supermatrix with only energy difference between orbitals on the diagonal, these eigenvalues will also be composed of the subtraction of energies of different pairs, different occupied and unoccupied orbitals. Make sense? Mary?
Yep.
Make
Yep.
sense?
Yep.
Does this make sense? Okay. So in the limit, if we neglect Coulomb interaction, then Cassida equation will reproduce the result of independent orbital approximation. In case we take into account Coulomb interaction, there will be some corrections, both in energies and in shape of excited state densities. So this equation, a little notation so that Latin indices from the beginning and from the middle of Latin orbitals are used for occupied and unoccupied orbitals in the community of researchers who were deriving these equations. We do not have to follow it all the time, but just be aware that if you see the like I, J, and K, it will stay for occupied orbitals. And if you have A, B, C, it will be empty orbitals. What else? So this middle equation will not correspond to TDDFT. It will correspond to TDHF, time-dependent Hartree-Fock. Okay? Because it explicitly takes this Coulomb integrals. And in some sense, density functional theory and all theories that are derived from it work quicker because it uses concept of functional derivatives, which and they can be tabulated before computation is started. So before we did use functional derivative of total energy in respect to density, so first functional derivative in respect to density, and it was given as potential for Kohn-Sham equation, right? Now we do need an object that corresponds not of the pair of orbitals, of 4 orbitals. So this can be extracted from the total energy, or total energy minus kinetic minus exchange correlation, by taking second functional derivative. So in some sense, the A and B terms in the Cassida equation are obtained as second order functional derivatives from total energy over the density. The procedure how TDDFT works, in some sense, reminds us DFT procedure. So it will be self-consistent loop, and at each step we take the density, take derivative, and then repeat the loop. Another note. How does transition density correspond to total density and perturbed density? In some sense, we can tell that it is total density minus density in the ground state, right? If you do so, we will pick up these off-diagonal transition densities and cancel diagonal elements. Suppose that we all have completed studies of theory and equations behind TDDFT, and we know the equation. Suppose we know how to derive it. Suppose that we do have a flowchart and computer code that allows us to find our two goals: transition density and transition energy. Does it help us produce spectroscopic experiments? Or not quite? Do we have spectral instruments that measure transition density? Maybe, but I'm not aware. Typical thing that we measure is spectra that can be formulated as follow-up of oscillator strengths. So the question, where is my oscillator strength in these equations or their solutions? Where are the practical observables? You accept this formulation? So it is our next little goal, how to extract transition density and transition dipole moment and oscillator strengths out of transition density. Any comments about the equations on the board? Who likes or who doesn't argue?
What does TR stand for?
Aha.
That stands for trace, right?
Yes.
Trace? Okay.
Yes. So
Okay.
if you have 2 by 2 matrix with ones on the diagonal and zeros on the off diagonal, what will be the trace of this matrix? Anyone?
The sum of the diagonals.
Which will be equal to?
Two.
Yes. So trace is sum of the diagonal, not B, C, D, right, thank you. Sum of the diagonal elements. So who is happy with the first equation on the screen? There is no trap, it's a simple equation, right? We went over it. So if you do have 2 orbitals which are eigenstate of our quantum system, we can formulate matrix element of any arbitrary operator, right? And matrix elements are needed anytime we make connection between our quantum calculations and experiment. Now, who is happy with second line? One.
Kind of.
Okay, so there is derivation and proof, and it is really quick. Proof, I may skip it, but it's give me a request if you want me to prove that matrix element or expectation value of operator can be equivalently found as trace of the density operator times operator corresponding to our observable. So this is a standard thing, and in the TDD-DFT, in the time-dependent density function theory, we need this way of converting results of quantum calculations with real life to find expectation values. Specifically, we, or anyone who does TDD-DFT calculations in practice, just by clicking on drop-down menus and finding spectra, practices this equation. So transition density is found as a solution of Cassida equation. O will be our dipole operator, and the result of this trace will be matrix elements of transition dipole, which can be converted into oscillator strengths, right? So anyone objects against this train of thought?
No.
So density, expectation value of dipole, and then the next step is oscillator strength. So a little, how are we doing this time? Now I see that we will do things in time. Maybe it's a little quick pace, but we are safe. We will finish. So I probably would skip writing on the board the derivation, but it is really quick and demand if you need. So we will consider density matrix in the simplest possible form, where we have only 2 orbitals, only HOMO and LUMO, right? So this is density matrix. And elements are HOMO, 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 LUMO, LUMO, which are occupations of these orbitals. And then 2 elements. Now they're not matrices, they're just elements. Transition from HOMO to LUMO, which would correspond to X, absorption, and transition from LUMO to HOMO, which would be emission. So this is raw density. This one will be operator of transition dipole in matrix form. Why does it have this form? Zeros on the diagonal, non-zero elements of the off-diagonal elements. Because only if system is converting from ground to excited, transition dipole are non-zero. Okay? So suppose, imagine me writing, or imagine anyone from the class coming and writing. So if we multiply these two matrices in a row by column fashion, then you see that row by column will parse only one element. So 0 times row ho is 0, d times row LUMO to HOMO will be d ROMO to LUMO. See, this is the first element. Then the second, third, and fourth. Right? No objections. Multiplying two by two matrices. And now we do practice trace, which means forget about off diagonals, add together diagonal elements. So we put matrix element of the transition density out of brackets, and inside the brackets we have element of density matrix that corresponds to transitions from LUMO to HOMO, and element of density matrix from HOMO to LUMO. Do you have questions or objections about math in this step? Do you have objections against multiplication of two by two matrices? Good. Now, how do we interpret this equation? How can we verbally explain it? Good. But any ideas? How would you...
Physical meaning?
Yes, physical meaning or practical benefit.
I think there's something to do with the fact that there's the LUMO to HOMO plus the HOMO to LUMO. So it makes me think that there's density elements where we're adding one going in one direction, one going in the other. Maybe?
So, okay, nothing wrong. I like your verbal formula. And Ben already started to say something.
Well, wouldn't it just make our life easier because that's where most of the density should be?
Well, okay, it's not wrong. Both of you have part of truth in the same. So, if in case the elements of transition density corresponding to HOMO and LUMO are larger, the expectation value of transition dipole element becomes larger as well. Right? So the values of transition density elements directly affect expectation value of transition dipole. Expectation value. Transition density gives transition dipole. And it is linearly proportional. Any objections on this statement?
No.
Okay. So as soon as your Cassida equation programmed in the Gaussian or games or Dalton or any other software gives you transition densities, immediately it is really short subroutine to compute transition dipoles. And for different eigenvectors of the system, there will be different values of these elements, and there will be different values of transition dipole. Therefore, different eigenstates, different excited states, are absorbing with higher or lower intensity. Okay, so practicing multiplication 2 by 2 matrices, and then as soon as we do have expectation value of the D, we can compute this expectation value of transition dipole squared, multiply by natural constants, and get oscillator strengths. In this writing, I do miss little angular brackets for consistency. I hope to fix it next year. But what do you want to observe any difference from what we had in the past for independent orbital approximation and what most of us are doing in the projects? Or do you see any suspicious things that may look as typos? What do you do not like in this expression? I count on Kevin because last time he was so good in identifying little things. So, what is strange or different, or what makes suspicion that it is a typo in comparison between this equation for oscillator strengths and the oscillator strengths that we reviewed at the beginning of the lecture, the transition dipole that you are practicing when you are computing oscillator strengths based on VASP?
Is it maybe the d squared?
Okay, something else in addition? We need to look only on the last line. So, do you expect anything different in natural constants? Probably
No.
not. So we need to look only on the initial notation for oscillator strengths, notation for transition dipole, or notation for transition energy or frequency. In your oscillator strengths file, for each transition, for each line in the spectrum, how many indices do you have? You have transitions between pairs of between orbitals. So you have index first orbital and last orbital. From LUMO to HOMO, or from orbital number 280 to orbital 281, right? So two indices, I and J. Good? Make sense? So you will write this equation in your reports. Okay. Where are my two indices I and J here? How many indices are by transition dipole? How many indices by oscillator strengths? What is happening? Why one? Where is my second index?
Well, because the diagonal matrices, we're only considering where the two indices are the same.
No. It is very simple, much simpler than anything else we did today. It refers only to this handwritten picture with orbital picture and excitonic picture. And note that symbol here is I capital instead of lowercase I and J. Yes? Good. Let me quickly scroll back to this figure. Yes. I was too quick. So if we are residing in the orbital picture, for each transition we have two indices, from HOMO to LUMO, from I to J. If we are in the excitonic picture, we have only one index for each transition, because it is from ground to excited state number 1, from ground to excited state number 2. Therefore, it is capital. So this super index hides inside all delicate information about how it is constructed. Make sense? Or no? Anyone wants to object? Okay. Either everyone is happy and agreeing, or no one cares. So because we are in the excitonic picture right now, because TDDFT gives solutions in the excitonic picture, there is only one index, and it labels different excited states. And for a lazy person, it is easier to put one index instead of two. So if we are looking onto practical aspects of using TDDFT, we still compute absorption spectra as function of transition energy, but our transition energies, delta E, have only one index, delta E sub I capital, and our oscillator strengths also have only one index, F sub I capital. Right? So here is equation for absorption spectrum based on orbital picture. Here absorption spectrum based on the excitonic picture. Do not look on this slide. So we do need to quickly look onto implementations of the TDDFT. So if you would have a couple of more meetings, we could make it as a part of the labs to run a little model in Gaussian and select drop-down menu in the TDDFT. So Mary and Ben, can you explain what are TD and root keywords in Gaussian if you are selecting TDDFT calculations?
Time dependent?
Yes.
Mm-hmm.
But which values should you put for TD and root when you are submitting Gaussian from, if you're preparing input file for Gaussian?
So that would be the number of your, would it be the strength of the oscillator strength that you're interested in? I don't
Number
really
of excited states, right?
Yeah.
The states that we account with I capital index.
Okay.
Right? And since TDDFT is a little more expensive than regular DFT, this number of excited states is typically not very large. If we are computing spectra with independent orbitals, we may have like 100 orbitals below HOMO and 100 above LUMO. And then number of excited states will be 100 by 100, like 10,000, right? What's a typical value of excited states that you request from Gaussian? From your personal practice?
I don't.
So you use templates provided by someone?
Well, probably.
Mary?
Yeah, I'm trying to remember. It's
Does it impress you by being like very large number, like 10,000 or a million?
no, it's not. I think it's a small number.
Yeah,
No,
it's
no.
like 100 or maybe 300, but if you go above, you use human patience. Good. Like about will be okay to put here. So go into Gaussian calculations, you select these keywords, and then it does generate your Gaussian.log file. Remember,
Yeah.
in the first part of the course, we were exploring output of Gaussian for Hartree-Fock calculations. And it was giving us the list of occupied and virtual orbitals, correct? Did you
Yes.
remember? When you select TDDFT as your option menu, instead of occupied and virtual orbitals, it will give the output of about the following format. So it will write excited state 1, and 1 is I capital equals 1, right? Then it will give the transition energy, which will be eigenenergy for this transition, like h bar omega sub I capital. And then it will give oscillator strength, which could be small. And then there will be really important information. Has any one of you seen this type of information before?
Mm-hmm.
So Mary did. Ben, did you ever look on the TDDFT output?
That looks familiar, yes.
Okay, good. So what is your interpretation? What is, if we remember that in this model of titanium hydroxide, number of HOMO is 24, what would be this index? What does it mean, in your opinion?
Wouldn't it be 1?
Well, this 24 to 25 means that first excited state is primarily composed of transition from HOMO to LUMO, from orbital 24 to orbital 25.
Yep.
With weight coefficient this much, meaning that 69, 70% are originating from this transition and 30% originate from some other transitions, but we just do not mention them here to save space. Make sense?
But your major contribution looks like it's coming from excited state 1. At least the number seems to be higher, right?
The excited state 1 is primarily contributed by pairs of orbital HOMO and LUMO.
Mm-hmm.
But it may include some other pairs of orbitals. If you go further, look on excited state 2, you see
that's right.
energy will be a little higher, oscillator strength is different, and now this excited state 2 corresponds of contributions from 2 orbital pairs, from 23, which will be HOMO minus 1, to 25, which will be, or from 23, which is HOMO minus 1, to 26, which will be LUMO plus 1. Okay?
Yep.
So, and already at this second excited state, the TDDFT conflicts with our orbital pictures. So it tells that second excited state will be superposition of at least two pairs of orbitals. So when we need a little higher precision, we go to TDDFT and use this fashion. And by the way, if you compare transition energies with offset between orbitals, this one will be different because there are corrections to total energy. In case we need huge number of orbitals or cover broader range for spectrum, we can make step back towards independent orbitals, but then we need to explain what has been neglected. So this effect of superposition of multiple electron hole pairs into given excited state is neglected.
Same.
So same information. Let's look on the same information once again. If we look onto the first excited state, it will be contributed only by this. We only have these elements. And if you look on the second, it will include HOMO minus 1 LUMO, like these elements. More elements on the off diagonal, more transition densities. So this arrow shows a state that corresponds to first excited state, and here are elements that will be non-zero in the computed transition density when we go to the second excited state. So in some sense, this x and y variables in Cassida equation, or this rho ij in the density representation, are summarized in a little bit human-friendly form in this little notes after excited state label. But if you need to explain for yourself, for your colleague, what are these numbers, you can refer back to transition densities. So, and since those are transition densities, there are no theorems that they have to be positive. They can take negative values as well, which is normal. Okay. Any questions about interpretation of the output of TGDFT and Gaussian?
No.
Okay. We can do it maybe after completing all important program, like last 5-10 minutes in the lab. It is really quick for small systems. Or you can try on your own, or I can distribute template files that you will run on your own. And if this information is fed into the equation for absorption spectrum, you'll see spectra that look, it responds first excited, second excited, it will look similar to what you get in the independent orbitals, but typically it shifts to a little lower energies. If one will plot independent orbital spectrum nearby, it will be blue shifted compared to more realistic TGDFT. So this is an example of absorption spectrum for titanium hydroxide from TGDFT. Here is equation which you may want to cite if you are practicing TGDFT for your research. Here is the photo of the designer of this equation. And here is the summary of this theory once again. So generally, Schrödinger equation can be formulated in time-dependent formulation, with time-dependent part. And in case the potential is time-dependent, if there is a time-dependent part which corresponds to optical excitation, then density or change in the density in respect to ground state will be composed as pairs of occupied and unoccupied orbitals, and this is notations of the original designer of the theory. Change in density, instead of rho he uses p, occupied and unoccupied, and those are x and y. So here is the Hasidic equation for eigenvectors and eigenvalue. Here are A and B coefficients which are expressed in terms of functional derivative, second functional derivative of the total energy in respect to density, or first functional derivative of the static part of the potential from Lorentz equation in respect to density. Here is the way how the elements of transition density are stored in the vector form and back, and one can practice same thing as we did before to set up a flow chart for TGDFT calculations. So as an input, one gives positions of ions, number of electrons, tolerance, and root, and how many excited states you want to find. And as an output, we do need transition energies and oscillator strengths, right? Because we need spectrum. But it will compute anyway the eigenvectors of transition density. So calculations will be done for all excited states with I less than the root. And there should be similar flow chart as we used for Hartree-Fock and for density functional theory. If time would be more generous to us, we would probably put stickers as we did before, but let's go quicker. So we solve Hasidic equation, we formulate total density as pairs of orbitals times this x and y transition density. And then we compute, based on this density, we compute A and B coefficients as second functional derivative of total energy in respect to density. And criterion of convergence is that we get convergence of the excited state energies. So if we are getting this convergence, we are going to the next excited state. If you don't, we feed in a self-consistent way this A and B coefficients into a Cauchy equation and solve it again. So there is a self-consistency cycle. As soon as we get convergence for a given excitation, it should be index I here and there. We go to the next I and repeat the self-consistent procedure for each excited state. And then we scan through all excited states under root. When this procedure is finished, we are getting set of excited state transition energies, frequencies, transition densities, and meanwhile the code computes transition dipoles and oscillator strengths, two things that we need for plotting computing spectrum. Make sense? Generally. Same thing, just in a little better handwriting or machine typing. Equation, connection between density and elements of this equation. One loop for update the energy of excitation, and another outer loop for going through different excited states. And here we are going through practice of the trace operation for finding oscillator strengths. So, in this course, we started from molecular Hamiltonian Born-Oppenheimer separation. Then we went for electronic structure through the simplest theory that takes into account electron interaction, Hartree-Fock theory. So it takes into account electron interaction and antisymmetry of wave function. And then we carefully practiced the steps needed for density function theory based on theorems and auxiliary universe where electrons do not interact with each other. And in the recent couple of meetings, we covered time-dependent density function theory. There were practical components of building models, optimizing geometry, finding density of states, ionization, and affinity, and absorption spectra. We will revise molecular dynamics and movies at the meeting tomorrow in the lab. And I think this concludes academic part of the course. So I'll stay here to answer any questions, but a program of today's meeting is done.
Awesome. Thank you.
Thank you.
All right. Have a good one.
Yep.
Understand what I do for this project.
Huh?
From your email, I didn't really understand what I have to do for this project. So you told me to read about VEAD last time. I read that. Maybe I understood that. In your email, you wrote something RFT. So I got confused. So RFT is not related to VEAD.
No.
That's just
No. So if you wonder about the class, great introducing of things like electronic structure before and after molecular. But to my understanding, you do want to merge class activity and your research.
I want to publish a paper.
And for this, you need to see how the lithium ions migrate upon thermal excitation of their redistributed space. Right? Is it correct?
Yes.
So there are so many lithium ions. And we need something, a summary of their behavior. So I suggest that we practice So we scan over all find the difference of distance between them, and at the values of R when this when this R equals to distance between two lithium ions, it will give a peaks. So if you make this RDF radial distribution function for perfect crystal, there's nothing in the first one in the distance is peak, and the second in the distance is near south. But if your model experiences redistribution, it may move or it may just get broader. But this broadening of radial distribution function would correspond to average drift of your lithium ions and their mobility. And I think it is something quick that we can do without I will just share some scripts that you can practice. This keyword is very tricky and dangerous. There is no guarantee that it will work. But if you may just try your luck. If it works, good. If not, you will not work. But you may right now you already have more. You can restart.
So,
Well, just wait.
NVT calculation and molecular dynamics both are same?
Huh?
NVT calculation?
Yes.
Both are same?
Yes.
Okay.
So you can restart molecular dynamics in a new directory, but add into the in-car, use in-car for molecular dynamics, but add 0.1 for whatever you find.
Like default value is 0.0.
Yes. If you use a little bigger value, it will be crazy, exaggerated, but if your field is too big, you may not see any changes. If it is a strong field, you will see some dynamics.
See what? RDF?
Teammates? Even do those inspect. Then sheet, and then you do MD, and then you do those inspect. Right? That is what you are planning right now. In addition, we can here and this is more than enough for the course. But if you really want to invest, get some points for the project, you may try additional bridge. That's so. And then after this, do again dose, absorption, and then you can compare 3 sets of bubbles. Okay?
Yeah, now
It's not like all possible problems in the world, but they are very limited time. And I think it is, even first line will work great for the course, but this is an extra that you can try as a high risk project.
Okay, I will try that. Like, I have done optimization, heating, and molecular dynamics simulations. Did you put? I got it.
With video.
Yes,
Video.
video.
You're able to do the same videos.
Yeah, I can.
Okay.
Will I do that for each of the steps?
For each molecular dynamics. If you do several molecular dynamics, make video for each of them, upload to YouTube and send them.
Okay, sure. Thank you.
Oh, please.
I will help you build plots to tomorrow, then we can build these simulations.
That's one thing that
What plot will you?
Yeah, those.
It's like, it's all like part-time. You could do like someday.
So,
Ideally, yes, but it will be not a big sin if instead you do this to save the step. You can go either this way or use heating from there, because during molecular dynamics anyway it will change configuration. And then it was here MD ground, here you do MD plus ferro, and this is most interesting. Out of here, you do single point, and SW equals 0. So you do not re-optimize after molecular dynamics, because then it will bring you back. It will be identical to here. Single point, and then do these two states and absorption.
For here, so I optimized, so this is what I did. We did Furry, and then I took the output of that and put it in optimize. That was wrong. Probably it wasn't needed.
No, you don't. Furry is optimized together, but after you complete it, do not.
Yeah, we did Furry last week. Okay, so I assume this was one step.
Like you have two sets of directories. One set of directories without Furry, another with Furry. With Furry, you put Furry everywhere.
Yep.
And
when it came to here, I thought we took the output of this to make Furry. No. Okay.
it's like two independent threads.
Okay. Yeah, so now I have to redo my stuff again, which is fine. And yeah, so I would just take our original optimized geometry with that Furry code and put it into heat.
Yes. Also, if what you are saying is best and correct.
Okay.
Yeah.
If we've never done tasks with these two together, how do you get this? Or
We should. I did.
yeah, if we did Furry, we can get these. Yeah, okay. So then I did an extra step I didn't do, which is fine. So then I'll do to heat to here. This, so we just run VAST with NSW equals 0.
And then Furry, here, there's a Furry, here is also Furry.
Yeah. So when we run this, so this is like the VAST calculation that should give us some sort of video, right? Okay.
Yes.
So then this single point, what is this doing?
I got your question, you know what to answer, just formulate the words.
Okay.
So, if you ground state and no Furry, you'll get something like this, right? If you use Furry with optimization, you get this one occupied, this will be unoccupied, something like this. So it will be similar to ground, but there will be population here and no population there. And after molecular dynamics in ground state, you get so same structure, but small and smaller. And if you will do molecular dynamics with gap will become tiny.
Okay.
Or no gap. So this is most aggressive environment that you ruin your system as entity and will bring depolarization and some most drastic changes in the signatures in the observables.
All right, let me take a picture.
Please.
I'm gonna write down.
So you did promise to do something good to Anis.
Yeah.
Huh?
This is the first price poster large.
A little bit, doesn't it?
Thanks, Dr. Killen.
My pleasure. Candidate, PhD candidate Erickson.
That's right.
Yeah.
Questions?
You have time to
Yeah, we just went over it.
Oh, okay, so the TV news and then really wait for it. Sure. Last
If anything,
What
because we didn't really understand that we were doing debug.
Okay.
And so
No, I wasn't doing debug, I was doing the proper one, but I was doing like 24 hours at it, and it still wasn't coming back to the number.
yeah, you probably could do a lot less. Even on debug, it was like giving us DOS with plots like this, and it was working.
I was waiting any of that until after I had gotten a successful completion. So we are getting a successful completion, looking at the Slurm file.
What is Slurm?
The Slurm file, so when you run a batch script, the Slurm file is the log file, the output from what you were doing. So I was going off the Slurm file because I thought that was how you checked to see if it was a successful exit.
You're probably right. I'm just saying.
But you were getting enough data back that it was still making sense and it was still generating something functional.
But all we did was DOS. That's all we looked at, or I looked at. And so I could be getting like
Okay.
barely any detail here, but you know how this flow, right?
Well, because normal what's happening is like, so it would be like halfway through an optimization. So yeah, it might just be clipping your graph. Here you might not be getting all the information, at least you're getting something.
Yeah, I was getting both sides actually, but yeah, like it was actually, you know, a lot bigger.
I guess that's kind of the stuff I wanted to ask. Just to make sure that the stuff is fantastic.
Yeah.
Because if I don't need to run it that long, and I don't need to run the kind of resources, and I can get this stuff done faster, that's all the better.
Yeah, I don't know. I mean, when it comes to
I'm just too unfamiliar with math. This is my first time touching it.
yeah, my luck of the draw is showing that these worked in debug, which it said that max 35 minutes.
Okay, so then I might, because I got pissed off enough after running a job for 1 hours, I deleted everything and that's
Yeah, I know the anger.
After I got done just wasting all the resources, and that's why I just wanted to really come.
Yeah.
Until I could talk to you.
I went through Rage, as you saw in that one class.
Yeah.
So I know that people, I mean, different issue.
When you say is that free energies?
Yeah, so it's so apparently it's like for me, which is Fermi energy, but it's weighted.
Okay.
And I don't know what the weighted means, maybe it's a statistical term, but
Probably because that's for, I guess my background is computer science, so I just decided that I was mathematics like this. That's mathematics.
Yeah, I don't know either, but that's what he told me, so that's why it's the W's there.
Okay.
So,
And then, yeah, so then in your in-car, you actually, because I think the in-car I have is actually doing the heating at my same time.
yeah, what he did something extra here, so this was like something he did last Wednesday for me. I think it might have been in-car for a reason.
Okay.
I think. The guys came in there. And then I'm just taking those outputs, heating them with Furby, and then MB with Furby and DOS and all.
Because I was waiting, I thought this was a whole separate run, so it was heat, the concurrent plus car.
Yeah.
And then if an electrodynamics, and electrodynamics run, and then you can start making graphs.
Yeah, so on every in-car, so I think this one was included, and for sure this one, and for sure this one.
Yeah.
On the in-car, so like let's say we're talking about heat, it's everything's the same except at the bottom add this line. F-E-R-W, and it gives you the numbers. In this case, I have 117. Put a star here. It's really complicated. And then something over here. And this is an extra line you have to add in to every in-car.
Okay. That was the one where we shifted something.
Exactly.
Okay.
That's exactly it.
So I may not be quite ready to actually decide which one I'm shifting. Mine would definitely have.
I think he looked how many electrons do I have? 118. And whatever this code does, it's shifting one from occupied, making it unoccupied, and putting one into
Occupied, or putting one where Lumo used to.
Yeah. Hellos, yeah, so from HOMO to, so whatever these numbers do, that's what it's doing.
So take,
So I had 118 in this case, 71 from, I don't know, yeah,
basically, you're
yeah.
one above.
And there's something else here, I forgot. So, but that's it.
All right.
Good luck.
Yeah.
This one is good. CH. It's something different. Then it's crazy. Yeah.
So, how that work?
I don't know. It's your other one. Just check. Just amazing. Should yes. You need to motion.
Get what is same. That optimized file I can use for everything.
As a sample to design a solution. Each directory will run different key.
Some saddle point. And again we're taking the saddle point.
Section brings you.
How those people's should somehow be on the mechanism of conversation. That's all right. Yeah, just like that's that then we can help you. So did you just again the statute and findings of this is one that has not like small. No, it was this version just
That's why I made this error. Yeah, just those information.
So it doesn't show you much orbitals, energies, and occupation.
That's why I wanted to